Welcome to Chapter 11 on gases. In this video, we will explore the properties of gases, the laws that govern them, and the models used to understand their behavior. This video will cover several key topics, starting with the kinetic molecular theory, followed by the relationship between pressure, volume, temperature, and moles, as described by various gas laws. The kinetic molecular theory provides a model for gases based on four postulates. Gas particles are in constant, straight-line motion, they do not interact with each other, there is significant space between particles, and their average kinetic energy is proportional to their temperature in kelvins. The kinetic molecular theory is a helpful model for understanding gas behavior under many conditions. While it is not a perfect description, it remains highly useful and accurately predicts gas behavior in most standard situations. For a visual understanding of these concepts, you can explore various simulations that illustrate the behavior of gases and the application of gas laws. This table summarizes the fundamental gas laws, including Boyle's, Charles, and Gay-Lussac's laws, as well as the combined gas law and the ideal gas law, showing the relationship between pressure, volume, and temperature. The ideal gas law is expressed by the equation PV equals nRT. This table defines each variable, including pressure, volume, temperature, the ideal gas constant, and the number of moles. Have you ever wondered how straws work? Or if there is a limit to how long they can be? Understanding gas pressure is key to answering these questions. Even with a perfect vacuum and ideal materials, a straw has a physical limit. A straw longer than approximately 10.3 meters would not be effective for drinking. Pressure is defined as the force exerted per unit area by gas molecules colliding with surrounding surfaces. At sea level on Earth, our atmosphere exerts an average pressure of 14.7 psi. When a straw is placed in liquid, the pressure inside and outside is initially equal. When you suck on the straw, you lower the pressure inside, allowing external atmospheric pressure to push the liquid up. Atmospheric pressure is limited in its ability to push liquid up a straw. A 10.3-meter column of water creates a pressure equal to the atmospheric pressure at sea level, establishing the functional limit for a straw. In summary, straws function due to the pressure difference created by sucking. The liquid rises until the weight of the column matches the opposing pressure of the atmosphere. This diagram reinforces the postulates of the kinetic molecular theory, showing particles in constant motion, elastic collisions, and the relationship between temperature and particle speed. Let's begin by examining how the kinetic molecular theory models gases. A key observation is that gases are highly compressible because there is a significant amount of empty space between gas particles, unlike liquids, which have very little space. Because the attractions between gas molecules are negligible and the particles are constantly moving, a gas will expand to fill the entire volume of whatever container it is in. This also explains why gases have such low density compared to solids and liquids. For example, converting 350 milliliters of liquid water into steam results in a massive increase in volume, occupying nearly 600 liters. Pressure is defined as the force exerted by constant molecular collisions against a surface. This phenomenon is why we can use straws, inflate tires, and even breathe. Atmospheric pressure also changes with altitude. As you climb a mountain or fly in an airplane, the density of air molecules drops, leading to a decrease in external pressure, which can sometimes be felt as discomfort in your ears. Quantitatively, pressure is force per unit area. It is directly tied to the number of collisions occurring, meaning that increasing the number of gas particles in a fixed volume will increase the total pressure. When there are fewer gas particles present in a space, the frequency of collisions decreases, resulting in lower pressure. Scientists use several units to measure pressure. The atmosphere, or ATM, represents the average pressure at sea level. The SI unit, however, is the Pascal, with 1 atmosphere equal to 101,325 pascals. Another common unit is the millimeter of mercury, or mmHg. This originates from the barometer, where atmospheric pressure supports a column of liquid mercury to a specific height. Because 1 atmosphere of pressure supports a 760 millimeter column of mercury, 1 atmosphere is equivalent to 760 millimeters Hg. This value is also known as 1 torr, named after the inventor of the barometer. When performing calculations, you will often need to convert between these units. Be sure to reference the conversion tables provided in your textbook to ensure your units are correct. Here is an example showing how to convert 0.311 atmospheres into millimeters of mercury using these standard conversion factors. These principles are vital in daily life, such as in aviation. High-altitude flight requires pressurized cabins because natural atmospheric pressure is too low for human health, leading to oxygen deprivation. To maintain safety, aircraft use pressurized air from their engines to keep cabin conditions stable, generally keeping the effective pressure above that found at 8,000 feet of altitude. Finally, we must consider Boyle's law. It states that at a constant temperature, the pressure of a gas is inversely proportional to its volume. Decrease the volume, and you increase the pressure. Boyle's law can be demonstrated with a simple air pump. On the upstroke, increasing the cylinder's volume decreases the internal pressure, drawing air in. On the downstroke, decreasing the volume increases the pressure, forcing the air out. You can visualize this using a J-tube. Adding mercury increases the pressure on the trapped gas, which in turn causes the gas volume to decrease as shown in this plot. Molecularly, this happens because decreasing the container's volume crowds the same number of gas particles into a smaller space. This increases the frequency of collisions with the walls, thus raising the pressure. Boyle's law is critical for scuba divers. Because external pressure changes with depth, divers use a regulator to ensure the air they inhale matches the pressure surrounding them at that depth. For instance, at a depth of 20 meters, the total pressure is 3 atmospheres, 1 from the atmosphere itself and 2 from the weight of the water. The regulator must deliver air at 3 atmospheres. This creates a danger when ascending. If a diver holds their breath while moving to the surface, the air in their lungs will expand rapidly as the external pressure drops, which can lead to severe injury. Because the pressure decreases by a factor of 3 when rising from 20 meters to the surface, the lung volume would triple, which is why divers must always ascend slowly and breathe continuously. We can use Boyle's law to calculate these changes. Given an initial pressure and volume, we can find the final volume if the pressure changes, using the formula P1V1 equals P2V2. In this example, we calculate the final volume when pressure drops from 4 atmospheres to 1 atmosphere. The result is a simple verification that lower pressure corresponds to a larger gas volume. Have you ever seen cartoons where characters use long reeds as snorkels? It turns out this wouldn't actually work in real life, and we'll look at the chemistry behind why that is. If a diver attempted to use a long snorkel, the high external pressure at depth would compress their lungs. Breathing air from the surface would be impossible because the pressure gradient would force air out of their lung. Moving on to Charles's law, we examine the relationship between volume and temperature. We can explain why hot air rises. As temperature increases, the volume of a gas sample increases at constant pressure. This is the principle behind hot air balloons. Heating the air makes it expand, which decreases its density. Because the hot air is now less dense than the surrounding air, the balloon floats. To observe Charles's law, you can measure the volume of a gas sample at constant pressure while varying its temperature, illustrating the direct relationship between these two variables.